Hi, everyone. Thanks for listening to the Founder Spirit podcast. I'm your host, Jennifer Wu. In this podcast series, I interview exceptional individuals from all over the world with the Founder Spirit, ranging from social entrepreneurs, tech founders, to philanthropists, elite athletes, and more. Together, we'll uncover not only how they managed to succeed in face of multiple challenges, but also who they are as people and their human story.
The main thing that attracted me to physics was the fact that I was a very curious child. I asked myself and others many questions. I wanted to understand how things work at the most fundamental level. It has to do with what we are. Where do we come from and where do we go? It was a fantastic time, perhaps the most wonderful and exciting time of my professional life. The Higgs boson is a very special particle. The Higgs field permeated the universe millions of seconds after the Big Bang. Without this, atoms would not exist as stable entity, and so we will simply not be here. Usually people are called by research committee. And when I was called, my answer was no. I want to continue to do research. The last thing I wanted is, our goal is not to run big theory. Our goal is to answer the open question. Now, of course, if you ask me what will be your wish list, of course, for me, the most extraordinary thing would be to discover the particles that makes up the dark matter.
Joining us today is the dedicated Fabiola Gianotti, an Italian particle physicist and the first female Director General of the European Laboratory for Particle Physics, aka CERN, home to the world's largest and most powerful particle accelerator, the Large Hadron Collider. An experimentalist, Fabiola first came to CERN 30 years ago as a researcher. She was the head of the ATLAS experiment at the time of the monumental discovery of the Higgs boson, the last fundamental piece to complete the standard model of particle physics. Author of over 500 peer-reviewed publications and a member of several international scientific committees, Fabiola received 15 honorary doctoral degrees from universities and holds numerous awards, including the Special Breakthrough Prize in Fundamental Physics, the Fermi Prize of the Italian Physical Society, and the Tate Medal of the American Institute of Physics for International Leadership. She is also named among the top 100 most inspirational women by The Guardian newspaper and Personality of the Year 2012 by Time magazine. Just how did a classically trained pianist manage to break the glass ceiling and head up one of the world's largest and most respected center for scientific research? Well, let's talk to her and find out. Hello, Fabiola. Welcome to the Founder Spirit podcast. So wonderful to have you with us today, and thank you for taking the time.
Hello, Jennifer. Thanks for the invitation. Very happy to be with you today.
Fabiola, growing up in Italy, what were some of the major influences on your life?
Well, I think, first of all, I was exposed to a very broad education spanning from classical literature, history, ancient Greek and Latin, to a bit of science. So arts, a lot of arts. I remember many visits to museums with my parents when I was a kid. The cultural environment of Italy had a very strong impact on my life.
So you had an interesting combination from your parents, because your father was a geologist and then your mom had passion for music, as I understand.
Yeah, and she had studied literature. So I remember very interesting discussions at home when I was a kid, spanning many different topics. I remember when I was a small kid, I wanted to become a geologist, of course, as my father, because I was passionate and I was attracted by volcanoes and other explosive and, violent phenomena in nature. At the same time, I loved music and I loved literature. I loved art, I loved history and philosophy. So it was really good to have all these multiple passions, but then at some point you have to choose. And of course, it becomes a bit difficult because you realize that by choosing a specific path, you will have less time to devote to the other interesting things.
So you attended a humanities high school in Milano. As mentioned, you studied history, you studied art, philosophy, literature, languages, and with very little exposure to math and physics. And on top of that, you studied piano at the Milan Conservatory. So what inspired you to pursue particle physics at university, essentially studying something that is so infinitely small that is beyond our human perception?
So the main thing that attracted me to physics was the fact that I was a very curious child. I asked myself and others many questions, and I wanted to understand how things work at the most fundamental level. I used to ask myself questions about the universe, about stars. Everybody likes to look at the sky at night and see the beautiful stars and beautiful luminous objects. But for me, there was something more profound than that. I wanted to understand what is behind that and where that comes from. And despite my education in physics and math was very limited because kind of school I was attending was mainly a humanities school, I had this intuition that physics would allow me to answer those questions or understand a bit more about how things work at the most fundamental level. And then, so that's why I decided to study physics at the university level, and also to study later on particle physics, because particle physics is the most elementary of all sciences, because it studies the smallest constituents of matter in the universe, the so-called elementary particles, objects that cannot be cut into smaller pieces. And particle physics studies also the most fundamental laws of nature. This really satisfied my wish of understanding how things work at the most fundamental level.
So thanks to a postdoc fellowship, you arrived at CERN 30 years ago. And CERN was founded in 1954. There are 2 questions on its homepage. What is the nature of our universe and what is it made of? So before I go any further, can you explain to the audience CERN's mission and what it does exactly?
So CERN has 4 main missions, or if you want, as a mission that rests on 4 pillars. The first one is, of course, research, fundamental research in particle physics. And in order to study the smallest constituents of matter and the universe, you need big instruments. You need particle accelerators and particle detectors, and you need big computing infrastructure. The smaller the structure you want to study, the higher the energy you need to inject into the system to see the smaller structure. So to study human cells, a microscope in a lab is enough. But if you want to study the smallest constituents of matters on physical scales of smaller than a billionth of a meter, then you need big accelerators that smash them at the highest possible energies to be able to probe matters at the smallest level. So this is what CERN does, studying the elementary particles, the smallest constituents of the universe, but also building the instruments that are needed to accomplish this very sexy objective. So big accelerators, so big technologies. CERN is also a driver of innovation because we need new technologies in many fields, from superconducting materials to big data, from cryogenics and vacuum to sophisticated electronics. And so our second pillar is pushing the limit of knowledge. Our third mission is to train people. At any given time, we train 4,500 young people, including physicists, engineers in many fields, and technicians. And last but not least, CERN is a peace builder. One of the CERN initial goals by our founding convention was to be a kind of glue, fostering interactions and collaboration between people from all over the world. And today we have a population of 17,000 people, representing more than 110 nationalities. And some of these people come from countries that are in conflict.
So I also wanted to mention that CERN is the birthplace of the World Wide Web, MRI, magnetic resonance imaging. Both inventions are not to be overlooked in today's world. And the universe is estimated to be 13.8 billion years old. Why does it matter to go back so far in time to uncover the mysteries of the universe?
Because it has to do with what we are. Where do we come from and where do we go? And so it has to do with our origins. It has to do with evolution that we don't yet understand fully, which took us from a quantum fluctuation in the primordial vacuum two clever human beings. And this is still a mystery to a large extent, but we have understood a lot since humanity started to look at into this problem. So it has to do with what we intrinsically are as human beings.
I love that. I think that's motivation for a lot of physicists, actually, at least a lot of particle physicists, is to better understand who we are as human beings. The Large Hadron Collider, known as the LHC, the world's largest and highest energy particle accelerator, was built over a period of 10 years, and it was launched in 2008 in collaboration with over 10,000 scientists and hundreds of universities and labs across more than 100 countries. It lies in a massive tunnel of 27 kilometers in circumference and 100 meters deep underneath the French-Swiss border. And it's an absolute engineering marvel. So for those of us who live close to CERN, we're always wondering, like, what is actually happening inside this giant tube of superconducting magnets? Can you tell us, Fabiola, what is happening down there and what are we looking to uncover?
So what is happening down there is the following. So the Large Hadron Collider is a ring, a 27-kilometer ring, as you said, Jennifer, 100 meters underground. And what we do, we accelerate two beams of photons in the two opposite directions at the highest achievable energies, where the limit comes from the available technology, the technology of superconducting magnets, and we smash them at the highest possible energies. And the energy that we produce in the collision corresponds to the temperature that the universe had in millions of a second after the Big Bang. That 13.8 billion years ago gave origin to the universe. So we are able to reproduce in the lab the conditions that characterize the early universe. And so we can study what happened at that time. That was the time where the Higgs field and the Higgs boson started to act in the universe, thereby allowing matter, the matter we are all made of, atoms, to form. And so we are able to reproduce those conditions of temperatures. To give you an idea, that temperature corresponds to 100,000 billion times the temperature in the room I'm now.
Fascinating. We're going to get really geeky right now, or at least geeky in my definition, because I just got a crash course on particle physics by my 18-year-old son this weekend. So the standard model of particle physics is a theory which was developed in the early 1970s that describes the interaction of fundamental particles, which, as you mentioned, are the most basic building blocks of the universe. And it explains how quarks and leptons make up all known matter. So us, right? And also the computers. And how bosons are these force-carrying particles influence the interaction between the quarks and leptons. So I had a very good tutor. And one of these special bosons is the Higgs boson. And that was discovered at CERN in 2012. And you were the project leader for the ATLAS experiment. Do you recall the moment when you and the team realized that you might have hit the jackpot?
Oh, it was a fantastic time, perhaps the most wonderful and exciting time of my professional life, when you are close to a discovery and you realize that actually this fantastic particle is there. The Higgs boson is a very special particle. It's not just one of the many elementary particles. It's a particle that has special features. We call them quantum numbers in physics. It brings a new type of interaction and played an absolutely crucial role in the universe. The Higgs field, to which the Higgs particle is associated, a bit like the photon is associated to the electromagnetic field, played an absolute role because the Higgs field permeated the universe millions of seconds after the Big Bang. The elementary particles that were previously massless, like the photon, so they were traveling the universe at the speed of light, by interacting with this field, acquired a mass, and this allowed atoms to form. Without this, atoms could not exist as stable entities, and so we will simply not be here. So the Higgs boson is associated with something absolutely crucial for our own existence. Even after 10 or more years of studies, it remains mysterious because it's related to some of the currently open questions in fundamental physics. So clearly, it was not a moment when we realized that the particle was there. It was like a process in June 2012, from the beginning of June to the end of June, when we gave the announcement, where we saw the growing evidence for this particle in our data and the data of the CMS experiments, because Atlas and CMS together discovered this new particle, and it was absolutely fantastic. I remember sleepless nights. I remember emotion everywhere. I remember an absolutely crazy atmosphere at CERN where everybody knew, but of course that we were very close to something exceptional. But of course, we had to keep confidentiality because you're not until you are 100% sure, you cannot, of course, announce a discovery. So it was absolutely a fantastic time for me and for all the thousands of physicists from all over the world and engineers who had the chance of living that time.
It's interesting that the Higgs boson was nicknamed the God particle. And physicists just seems to me like a bunch of non-religious people. So why was it called the God particle?
Of course, we don't like this definition as a scientist, but it was nicknamed like that because of a book written by Leon Lederman, a Nobel laureate and US physicist, about the Higgs boson. And the publisher thought that a title for the book, like the God particle, would, of course, sell the book. And actually, this is not only sold the book, but also the particle, because people like to call it like that. But it's true that it's a very all particles are fundamentally important for the existence, for the universe and its evolution, our existence. But the Higgs particle is true that he had this very special role, and it's quite a peculiar elementary particle. And unfortunately, now recently Peter Higgs passed away.
Yes, so that's what I had wanted to ask you about as well, because the Higgs boson was proposed 60 years ago by 3 theorists, including Peter Higgs at University of Edinburgh, a Nobel laureate who passed away last Monday. And in remembrance of Professor Higgs, can you tell us what he was like?
So Peter Higgs was a very special person. Besides his monumental contributions to fundamental physics and to understanding how the universe works, Peter was a man of rare modesty, almost self-effacing. He was a very gracious person, very kind, sweet, caring. He was not one of those people who loved to listen to themselves. He was rather listening to other people, a great teacher. He would be able to explain physics in a very simple yet profound way. So we will sorely miss the man and the physicist.
Growing up, Fabiola, do you have a favorite physicist, or is there someone that you look up to?
Well, for me, when I was a young student at the university in physics, of course, Enrico Fermi is the Italian physicist, a brilliant model of a scientist. At that time, theorists and experimental physicists were essentially the same thing. And great physicists like Fermi were at the same time great theorists and great experimentalists. Now, the job is a little bit more specialized, and the theorist and the experimental physicist are 2 different categories, although, of course, we work with each other. And so for me, Fermi was the model. But I must also say that one other thing that pushed me into physics, when I was 17 years old, I read a biography of Marie Curie, and I was absolutely excited by what I read about her life and the fact that physics was such an integral part of her life. Her laboratory was at her home, so she would prepare the soup in the kitchen and then run in the lab to change the radioactive sample and then come back in the kitchen to finish preparing the dinner. So this idea that research is such an important and integral part of your life, a part of your home. Of course, I could not now bring the Atlas experiment to my home, but nevertheless, that really impressed me and had a huge impact on me.
Speaking of Marie Curie, in 2016, you became the first female Director General of CERN. I understand that you were called by the search committee to interview. Is that correct?
It's correct. The CERN Director General is something for which you don't apply. Of course, there is a job description, a job call announcement that goes up on our webpage, but usually people do not apply. They are called by the search committee. And when I was called, my answer was, no. I don't want to, I want to continue to do research. So I was appointed at the end of 2014. So we have to keep in mind that this was about a year and a half after the discovery of the Higgs boson, which was still today, but even more so at that time, a very mysterious and new particle. And I had finished my term of office as head of the Atlas experiment. And so I could now work directly with my own hands and with a team of young people on the measurements of the Higgs boson. So understanding how this particle behaves in all details. So it was a fantastic time. And the last thing I wanted is to do something else. So I resisted for some time. And then I went to the first step of the selection, hoping inside my heart that I would not be selected. And, but then at the end, when I was appointed, it was too late to decline. And so here I am.
Well, now you have to deal with finance, administration, HR, fundraising, and shuttling the diplomacy across 23 member states. And as a fundamental researcher, what was the toughest part of your job in the early days? Like, what did you really struggle with?
So first of all, I must say that I love my job very much. I must say that it's totally different from what I had wrongly imagined, because I still have the time to devote a large fraction of my day to scientific/technical problems. I of course, I cannot do research myself, but the scientific and technological and technical issues dominate my activity by far. So that's very important, because I'm learning a lot every day, and there is nothing more rewarding than going home in the evening and say, gee, how much did I learn today? So that's nice. But of course, I have to do with many other aspects, like interactions with the member states and other countries, the public, budget. But we physicists like to address challenges and solve problems. If there is no problems to solve, we get bored. And of course, in my job, in the early days, I was exposed to a new world on many new things, from finance, as you said, to human resources that were quite new to me. And so that was a challenge. But of course, that was also the exciting part. So I had to learn a lot of new things, and I had to learn fast.
So physics and science in general has been a very traditionally male-dominated field. Why do you think there's not more women in science?
There is a cultural bias still today. Some people, or generally society, think that physics and research in physics is not a job for women. Of course, there has been a lot of progress now. Things have changed. The fraction of women has increased. For instance, at CERN, when I joined CERN about 30 years ago, the fraction of female scientists was 8%. Today, we are beyond 20%. So there's been a huge increase, but we're not yet there. It's still a male-dominated environment, and this psychologically does not attract more women. Also, research is a very challenging field, and there are not always the good structures in place to support a balanced work-family life. At CERN, we have a nursery that welcomes kids from 4 months until 6 years. That's very good, but not all research institutions across the world have similar support for careers for men and women. So there are many steps to be undertaken to attract more girls to science, but also to support women's career in science, including instruction, but also making sure that men and women, they get the same salary, the same promotion and advancement for the same type of career and job. And this is something that we are really strictly monitoring at CERN.
So in terms of attracting the next generation, last year CERN launched the Science Gateway, which is an education and outreach center to explore science in this beautiful new building designed by that iconic Renzo Piano, the famous Italian architect. And I understand that this initiative is very dear and near to your heart. What inspired you, Fabiola, to undertake this endeavor?
So there were several elements that pushed me to undertake this project. The first one is that what we scientists learn does not belong to us. It belongs to humanity. And we need to share what we do more and better. So it's important that we, scientists, physicists in particular, in our case, make an effort to share with everybody, with the young generation, but with the public from all over the world, what we do, why it's important, what does it bring to society. So this was the goal number one. Goal number two related to that was that actually CERN used to host some 150,000 visitors annually, but actually we were receiving 300,000 requests. So we could not really welcome all the people who wanted to visit CERN. And this was for me a shame. So I was thinking of a new project that would allow us to expand our offer in terms of education and outreach to the general public. Those were the first two motivations for the Science Gateway. And the third one, and not less important, the goal of attracting more talents to science. Society today needs STEM talents. STEM stands for science, technology, engineering, and mathematics, because with the growing technology, the fast expanding technology, the number of jobs in STEM increases much faster than any other type of jobs. And yet, the fraction of high school students in Europe that decide to undertake STEM studies at the university level is still quite low. And so we wanted to increase the interest in science to, trigger curiosity in the young generation. So the Science Gateway is a big success. Now in 6 months, we have received more than 170,000 visitors. So we are well on track for reaching 300,000 annual visitors, and which testify to the interest in science in today's society.
Fabiola, I don't know exactly how many physicists that you have at CERN.
At CERN, we have two kinds of people. We have the CERN staff. This is mainly engineers and technicians with some physicists as well. And then we have the users from all over the world, and those are mainly physicists. So I will say the population of physicists about 14,000 people working at CERN. So it's a huge and immense amount of physicists.
That's impressive. The question I wanted to ask you is, what is it like to manage that number of physicists in under one environment?
It's a very good question, Jennifer, because, physicists are people who have a very free spirit. First of all, the fuel of science is curiosity and creativity. And this flavor can only expand in an environment which is a free environment with relatively little number of rules and top-down approach. And so I'm here to foster the work of the scientists at CERN from all over the world, the physicists, engineers, people who are here. And so it's very important to have, of course, we need to have a minimum of organization, otherwise such a big organization would not work. But this should not impede the creativity and curiosity of people. But actually, CERN has a very light hierarchical structure in the sense that if the youngest student has the good idea, then this is what CERN will pursue. So the leadership comes from ideas and not from the hierarchical structure. So that's important. It's also physicists, of course, are people who have strong opinions. Sometimes some of them are also a bit of a prima donna. So it's always not easy. But I must say that in general, we are all animated by the same passion for pushing back the limit of knowledge. So, and this passion is a glue that focuses all of us around the same objective. So I must say my job is very easy from that point.
So despite the discovery of Higgs boson, the standard model leaves still many open questions, such as the explanation of gravity, dark matter, dark energy, etc. And going beyond the standard model, CERN plans to build a much bigger accelerator called the Future Circular Collider, the FCC, by 2040. And if approved, it will be twice as deep and 3 times the circumference and smashing particles at 7 times the current energy of the LHC. So given the large cost of this project, why is it so important to continue to invest in science?
So, first of all, the FCC is one of the possible options for the future of CERN, is the preferred one by the particle physics community in Europe on average, although individuals may have different ideas. But the Future Circular Collider is the one that has been identified in the framework of the last update of our roadmap, so-called European Strategy for Particle Physics, as the most compelling. However, is not an approved project yet. We are at the level of the feasibility studies of geological, environmental, technological, financial feasibility. This being said, such an instrument like the FCC would be absolutely essential to allow us to make progress in our understanding of how nature works at the most fundamental level. So this instrument would be the most wonderful microscope that we will ever have built. If it is approved, this will allow us to address open questions from the dark universe to the family of elementary particles that seems to be quite chaotically and randomly organized. And we know that nature is simple, so we don't understand the fundamental things of nature. And so this instrument will increase it in a very major and significant way our capability of addressing and hopefully also answering those questions.
So what was really surprising to me, Fabiola, was in preparation for this episode, that in fact, we only understand 5% of the universe. So 95% of the universe is actually out there and we have no idea. It was a much staggering number than I had ever imagined.
Right. When you look at the sky at night and you see the beautiful stars and galaxies, what you see is only 5% of what is out there. The rest is a question mark based on form of energy and matters that we do not know. We do not know their composition, their origin, and do not interact directly with our instruments. So we infer their existence from indirect but very, very extremely solid measurements and proofs. 25% is dark matter, 70% is dark energy, and 5% is what we see. Matter, atoms, chemical elements, the same of which we are made. So clearly, on one hand, this is a little bit embarrassing. After so many centuries of exploration, we only know 5% of the universe. On the other hand, it's very exciting because it means there is still a lot to discover. And this means that we have to pursue research and exploration.
I also think that sometimes when you realize that the universe is 13.8 billion years old and we're only on this planet for less than 100 years, it just puts things in perspective. Yeah, whatever problem that we might be struggling with today, it seems very, very, very small to me.
Yes, we are just dust and we are very, very, very small in a very, very big universe, which is a size of 10 to the 28 centimeter, 10 to the 28 zeros. And still a lot of mysteries about what happened before and what will happen later on. But particle physics, together with other branches of science, of physics, cosmology, astroparticle, astrophysics, will help us make progress in understanding the past and the future.
Fabiola, you had mentioned at the beginning that studying particle physics, you were hoping to better understand who we are as human beings. Do you feel that after 30 years at CERN that you understand better about humanity?
Yes, but it's a very good question, Jennifer. I think yes, but maybe not because of what I learned about physics. First of all, the discovery of the Higgs boson, as I said, allows us to understand how matter was formed in the universe, so how atoms were formed, and so also our being here. Understanding humanity and human beings, I learned a lot in my capacity, maybe as in head of the Atlas experiment or now Director General of CERN, but also throughout my scientific life to interact with people from all over the world. And it still is a fantastic adventure. Being at CERN for so many years allowed me to grow not only as a physicist, but also as a human being in a very open, inclusive, tolerant environment. So that was really something special. So yes, I learned a lot about how diversity is really an asset of humanity, and we should really leverage more on this, being more inclusive and do all our best to reducing the gap, the digital divide, the wealthy countries and the developing countries traveling at two different speeds. We have to do our best because humanity's richness comes from our diversity and our, cultural diversity, diversity in terms of tradition, history. That's really is a very strong asset of humanity.
I love that. That's where your humanities background comes in, I see. And the influence from both your father and your mother. I know it's pure speculation at this point, but I was wondering if you might have an idea of what we might find next at CERN beyond the standard model.
Yeah, as you say, it's speculation. We don't know what nature has established at the energy scales that we are now exploring with the Large Hadron Collider, and we will be exploring with a future project at CERN. Difficult to say, although there are many theoretical scenarios that physicists, theorists have developed, and some of them are very compelling, beautiful, and have actually guided the design of colliders and the design of the experiments. Nevertheless, our goal is not to run behind a specific theory. Our goal is to answer the open question. For instance, there are many, many theories that explain dark matter, but nature may have chosen a completely different pattern, different way. So we have to remain broad enough in our research, in our exploration, in the way we build our instruments to be able to detect any sign of new physics or answer to those questions that nature has put in place. Now, of course, if you ask me what will be your wish list, of course, for me, the most extraordinary thing would be to discover the particles that makes up the dark matter. If dark matter is made of relatively heavy particle with weak interactions, those particles could be produced at CERN by the Large Hadron Collider with more data, or by future project. On the other hand, if dark matter is made of very, very light particles, then other approaches are more suitable. But of course, being able to produce here underneath the French and the Swiss borders, the particle that makes up 25% of the universe. So increasing our knowledge of the universe from 5% today to 30% in the future will be an extraordinary accomplishment.
And do you think we'll ever find the theory of everything, this unified view of the universe?
I think so. Not in the short term, though, but I think so, because there are many, many hints that at the most fundamental level, at the smallest scale, at the highest energy, forces are unified. And so this is actually what we try to do with our exploration at CERN, to find the common source that is behind everything we see. So I'm hopeful, but maybe it will not be within my lifetime. Surely not. But at some point we will get there.
That's good to know. As a physicist, or as a particle physicist, at this point, we have to be very optimistic that we will hopefully find the theory of everything. Fabiola, in the last century, with the invention of the atomic bombs, physics was really arguably the greatest map drawing force post-World War II. And how do you think the role of physics has evolved over the past decades as it relates to politics and society?
So first of all, the last decades had shown, in particular the last few years with COVID, for instance, has shown how fundamental science is for a sustainable development of society and planet. Today's global challenges, from health to climate change and environment, are complex, of course. Science is not the only element. Policies are important. Politics is important. But we cannot think of addressing those challenges without the help of scientists. Science was absolutely fundamental to get through COVID. The origin of those vaccines is actually fundamental research in the early 2000s. So this shows again the importance of pushing the frontiers of knowledge. And then when the time comes and you need it, you take out of your drawer and it's available. That's why I think it's very important that politics avails itself of the advice of science. During COVID, many governments actually put in place scientific advisory committees that help them face the pandemic. However, we should be careful and not, ask science to help us when a crisis materializes, but actually anticipate the crisis by constantly having science work hand in hand with politics.
I have a question about artificial intelligence when we're speaking of science and technological advancement. And it's a two-part question. So the first part is, how will CERN utilize artificial intelligence internally? And the second part is, externally, how will AI influence physics, if any?
So we are already using artificial intelligence at CERN in various domains. Some of the accelerator operation are already automatized and they use expert systems. We also use intelligence algorithm in the analysis of our data, when very often we have to extract a tiny signal. The Higgs boson is a tiny signal compared to the huge background coming from other known processes. And so for this multivariate analysis, artificial intelligence, machine learning are the best way to optimize the analysis. And no doubt that progress in artificial intelligence will serve CERN in the future as it will serve humanity. I think it's very important, and this is an ongoing debate, that we put in place all the policy that can regulate the development and the use of artificial intelligence, as many other technology. Nuclear physics led to the bomb, but it also led to nuclear medicine, which saved the life of millions of people. So that scientific and technological developments are used to serve humanity and not to go against humanity.
And now if we were to move beyond AI, which field do you think will lead the next scientific revolution?
If we talk about technology, clearly quantum computing, quantum sensors have a huge potential to have a huge impact on society. And this allows me also to go back a little bit to the importance of fundamental research. Quantum mechanics was developed at the beginning of last century and was considered to be completely useless knowledge. It even raised a lot of question about its validity. So at CERN is the largest quantum mechanics laboratory in the world that we do quantum physics and data. But these laws are completely different from the laws that govern our world, size, the dimensions we are confronted with. And sometimes there are paradoxes in quantum mechanics that are difficult to grasp for our brain. So quantum mechanics was really considered like general relativity to be useless knowledge. And yet, without quantum mechanics, modern electronics will not exist. Without relativity, our GPS will not work. Now we are talking about quantum computing as the next step in technology. So this is an example of how fundamental research has really led to huge breakthroughs with huge impact on society, sometimes not in the short term, in the longer term. And so funding fundamental research is really the best long-term vision for the long term.
And as the daughter of a string theorist, I have to ask you this question. Do you believe in the multiverse?
I'm an experimental physicist, so I'm very much driven from what I can measure. And for the time being, we cannot measure the existence, or we cannot really have evidence of the existence of the multiverse. So this remains as a possible hypothesis, which is not excluded, but I prefer an explanation, a physics explanation. As I said, as an experimental physicist, I limit myself to what I can explore and measure.
I knew that's what you were going to say, by the way. I knew it.
Well guessed. Well guessed.
You had mentioned earlier Enrico Fermi, and as your much admired physicist, and given how much media coverage there has been on the three-body problem, I don't know if you've seen it, and you're also the recipient of the Enrico Fermi Prize. So I wanted to know, what is your take on the Fermi paradox? Do you believe in other intelligent life forms on other planets?
So it's difficult to imagine, given the size of the universe and the complexity of the universe, the numbers of systems in the universe from planet to galaxies, that there is only one little planet in this huge universe where the conditions for life have emerged. But again, this is something that today is beyond it, but it's difficult to give an answer, although for me it looks reasonable and logical that there is something else.
I want to go back to your artistic talent. You recently accompanied the famous cellist Yo-Yo Ma on the piano as a duet. And also on YouTube, there's a video that I found from a few years ago in Davos where you and Yo-Yo Ma talked about the connection between art and science and how they connect us. So I'll make sure to include the link in the show notes. And most people will agree that art is beautiful. But Fabiola, where do you see the beauty in science?
Science is as beautiful as the arts. Physics is beautiful. So, first of all, nature is beautiful. When we look at the universe and the complexity of nature, we found it clearly beautiful. But science, in particular physics, has some inherent beauty at the very foundation of its laws. If you look at the fundamental laws of nature, those that we study in particle physics, they are based on principle of symmetry, so principle of beauty, aesthetical principle. The equations themselves, the mathematics, which is the language of the universe, is beautiful. The equations of quantum mechanics, or the equation of the standard model of the equation of general relativity, is really aesthetically beautiful. So it looks like nature has chosen beauty as one of its founding principles. Music, like physics, are a manifestation of complexity. You think about a symphony or an opera, Wagner opera, very complex. At the same time, they build on just a few notes or just a few particles, particles in physics. So complexity built upon simplicity is another common theme.
I really love that. One last question. Your directorship at CERN has been renewed for a second term, and you became the first person to be appointed for 2 terms. What would you like your legacy to be?
I will be very happy if by the end of my term, I could have contributed to expanding CERN mission in all its facets: research, technological development, training of the young generation and education of the public. Science Gate is an example, and being a model of collaboration across borders. I think CERN has made huge progress over the past 20 years, thanks to our collective work, the work of 17,000 people from all over the world. And I hope that this is the basis for the next big project at CERN and for our next big endeavor.
Great. We're now coming to the end of our interview. And as you know, we end every episode with a quote. And for this episode, we have a quote from Brian Cox. And just like you, he is also an experimental particle physicist and a musician. We are the cosmos made conscious, and life is the means by which the universe understands itself. Fabiola, I want to thank you very much for coming on the Founder Spirit podcast today and taking us through the wonders of the universe. Thank you so much.
Thanks, Jennifer, for the excellent questions.
If this podcast has been beneficial or valuable to you, feel free to become a patron and support us on patreon.com. That is patreon.com/thefounderspirit. And as always, you can find us on Apple, Google, Amazon, and Spotify, as well as social media and our website at thefounderspirit.com. I'm partnering with the Wheeler Institute, a nonprofit foundation focused on accelerating the transition to a net zero economy in restoring planetary health.